All right. What if you're estimating a population mean, but you don't know sigma? Okay, first of all, how likely are you to know sigma? Well, if you don't know mu, which sigma is the sum of each value minus mu squared, all divided by n minus 1, and then you take a square root, okay? So, if we don't know this guy, how on earth do you think we would know this guy? And the reality is, chances are we don't. And so, in all the free response questions that has ever been given, there's only one time that they gave you sigma. Okay? There's been dozens of times that they've not given you sigma. Okay? And so, most of the time, we will be without sigma. All right, when estimating a population mean. So our best guess is the sample standard deviation. So this is the standard deviation of all my x's, okay, which we calculate using this formula, basically plugging in x bar for this. And if we do that for every single thing, we're going to get Sx instead of sigma. All right. But now the problem is this Sx is less reliable. It's not always going to be consistent. And if I have an unusual sample, I'm going to get a big or potentially a small standard deviation. And so there's a lot more variability here. Okay. So we're going to use something. We're going to use this standard deviation divided by the square root of n. And that's just like sigma divided by the square root of n. This is sigma of x bar versus what we call standard error, which is s divided by the square root of n. Okay? So this is when we get to use z and the z distribution and the z stuff. Here, we're stuck using what's called a t distribution and t star. Okay, and so there's a dividing line, and really it's, do we know sigma? If you know sigma, you're on this path. If you don't know sigma, you're using the standard error, and you're going to be using a t distribution. Okay, so if our standard deviation varies from sample to sample, will we be able to use a normal distribution in a z table? No, we need this family of distributions called the student t distributions. And we'll watch a video in class that shows why it's called student t. But the degrees, there's something called degrees of freedom, and it's equal to my sample size minus 1. And you'll see that on our t table in a second. But why do I call it a family of distributions? Because the z distribution, standard normal, is tall and skinny like this. But the t distribution is a lot wider. See how there's a lot more out here, right? This one has a lot of probability up in the top that the red one doesn't have. And really, for a really small sample size, it really has a lot out here in the tails. Do you see all this extra probability? And in this one, there's all this extra outside in the tails. You're a lot more likely to have a sample that's more than just 2 or even 3 standard deviations away from the mean, okay? And so you tend to see some larger values than what we're accustomed to with the z-table. There's a lot more variability because not only is my x bar varies, but my standard deviation varies. So there's double variability, it seems like, okay? So let's take a look at the table real quick. So if you go to your tables, you can look here. There's the z table on the left for the negative z values. There's the z's for the right, the positive z values. And now here is the student t distribution, okay? And notice they talk about the probability p is what this tail probability is. So if there's 25% on the right, or 20% on the right, or 15%, 10, 5, right? So they show that with different degrees of freedom. Okay, the degrees of freedom, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It goes all the way up to 30, and then it starts going by 10s, and then 20s, and then 900, and then up to infinity. Okay, so tail probability, 0.025. Notice down bottom is associated with a 95% confidence level. So remember how when we were studying this, how we said you take 1 minus c divided by 2? Gets you that. And for a 90%, 1 minus 9.9 is 10%, divided by 2 is 0.05. So that tail probability, this is the tail probability associated with this confidence level. When you're at this confidence level, that is how much is in each tail, okay? And so both of those two things are beautifully related there. But notice, this infinity row is basically a z-table, okay? This is the z-table. Remember the 95% confidence level was 1.96, and the 90% confidence level we said was 1.645. These are your z-stars. You don't need to use the stupid z-table to find your z-stars. They're right here, hidden at the bottom of the t-table. But we will use this. So like if I have a sample size of 15, my degrees of freedom would be 14, n minus 1, and the 95% would be a t-star of 2.145, okay? And that's how we read that. So let's try a problem with this. Oh, how does it change my confidence interval? That's an important question, Mr. Granz. So normally we take x bar plus or minus z star times sigma over the square root of n. Well, if I don't know sigma, what do we use instead? We use the standard deviation. Well, now that I've used the standard deviation, this isn't the standard deviation of my x bars. This is now my standard error. And I can't use z star anymore. I need to use t star. And that's all that changes. You're still using x bar as your point estimate, but your margin, whenever this changes to standard deviation of my sample, and then this is now standard error, we need to use t star, okay? So, auto pollution, environmentalists, government officials, vehicle manufacturers, all interested in studying auto exhaust emissions. The major pollutants in auto exhaust from gasoline engines are hydrocarbons, monoxide, and nitrogen oxides, okay? There's a table that has all the data in here. I've already put the data into my calculator, stat, edit. You can see it here in, or no, this is just the summary statistics. I didn't put the data in there yet, okay? There's my X bar, there's my S, all right? So you still wanna go through panic, okay? So what parameter are we trying to measure? We're trying to measure the true proportion, not proportion, the true mean NOx levels of emission, okay? The assumptions, we need random. Well, it was a simple random sample was taken. It's not listed here, but the data is in your book, okay? Independent, well, you would need to know that there were 46 cars, and so as long as there's at least 460 cars, we're in good shape. And then would it be relatively normal? And here is where we need to be careful, okay? The central limit theorem works for normality to the point for z distributions, but for a t distribution, we'll talk a lot more about this. It's not robust against really, really messed up data sets. And so this requires a lot of calculations and those wonderful friends of ours called the normal probability plots. And just really, if you don't have a normal population, you really want to make sure that you have a relatively normal sample, at least symmetric, not drastically skewed, definitely no outliers or massive outliers. Otherwise, you're really sacrificing normality, okay? So this one, proceed with caution, okay? And that's something you'll see a lot in these problems. So name the interval. So we're doing a one sample t interval, and my interval, you take my x bar plus my t star times the square root of the sample standard deviation divided by the square root of n. So we have 1.329 plus or minus the 2.021. Well, where'd that come from? Well, my sample size was 46, so we're going to use 45 degrees of freedom, okay? Oh, wait, there is no 45. Well, we just picked the one thing smaller than it. And you can see here in that 95% column, it's 2.021. And so that's where I got that T star from, okay? Times S divided by the square root of n. And we get 1.329 plus or minus this margin of error gets me this interval from 1.185 to 1.473. All right. And then you want to write a conclusion that says we're 95% confident. 95% confident that the true mean NOx levels is between 1.185 and 1.473 parts per million. Okay, so there's a lot more we need to talk about, and the real biggest part that I'm going to really try and address in class is this. What do we do about this normality condition? Okay, still needs to be simple random sample, still needs to be 10%. But this T star changes where you're looking at your T table with n minus 1 degrees of freedom whenever you don't know sigma and you use the sample standard deviation. Okay, so good luck and farewell.